Measuring the mass of atoms. A single atom can't be weighed on a balance. However, the mass of one atom can be compared to the mass of another atom using a mass spectrometer. And a mass spectrometer is an instrument in which atoms or molecules are ionized and then accelerated. The ions then are separated according to their mass. Now, since we are comparing the masses of atoms, the values we obtain are relative values and not actual values. So we need to set a standard atom to compare the other atoms to it. So the element carbon was chosen as the standard atom. And it was chosen because there are 4 more compounds containing carbon than any other element. So now the masses of all atoms are compared to the mass of a carbon atom. And this comparison gave us a series of values for the relative atomic mass for the different elements. The relative atomic mass is the average mass of atoms of an element, on a scale where the carbon atom has a mass of exactly 12 units. However, after analyzing the masses of various elements, a little problem showed up. And the problem was that pure samples of many elements, like for instance carbon, hydrogen, and chlorine, are found to contain atoms that have different masses. And this is despite the fact that these atoms have the same numbers of protons and electrons. So what is it that's making these atoms have different masses even though they are from the same element? The studies have showed that the different masses observed are the result of the presence of different numbers of neutrons in the nucleus of the atom of the same element. And when this occurs, the atoms of the same element are called isotopes. And isotopes are simply atoms of the same element that have the same number of protons and electrons but have a different number of neutrons. Some of them are even radioactive because their nucleus is unstable. Like hydrogen, for instance. Hydrogen normally has 1 proton and 1 electron only, but sometimes a hydrogen atom could contain 1 proton, 1 electron as usual, and 1 neutron. It's called then deuterium, and it's still a hydrogen atom. It's just an isotope of the most common hydrogen atom, which has 1 proton and 1 electron only. Hydrogen also could have 2 neutrons, and 1 proton and 1 electron. It's then called tritium. This is also an isotope and it's still a hydrogen atom. The isotopes of an element are defined by their difference in mass number. The isotopes are also referred to by using their mass number. For example, the isotopes of hydrogen are hydrogen 1, hydrogen 2, which is deuterium, and hydrogen 3, which is tritium. And the number 1, 2, and 3 represents the mass number. For instance, which of the diagrams A, B, or C represents the nucleus of an atom of carbon-14 isotope? Well, diagram A has 6 protons and 6 neutrons. That means this is carbon-12. The diagram B has 6 protons and 8 neutrons. That means this is carbon-14. And that is the answer for this question. And diagram C has 6 protons and 7 neutrons. That means this is carbon-13, and that is a wrong answer. Nucleon is a term used for protons and neutrons. So an atom of neon has 10 protons, 11 neutrons, and 10 electrons. How many nucleons does it contain? Well, we have 10 protons and 11 neutrons. This means we have 21 nucleons. It is the number of electrons in an atom that determines the way in which the atom forms bonds and react with other atoms. So the isotopes of an element have the same chemical properties because they contain the same number of electrons and therefore the same electronic configuration. However, some physical properties like density and rate of diffusion are different for the isotopes because the mass of the atom differ. A visual illustration of how the presence of isotopes affect physical properties is the difference in density between ordinary ice and heavy water ice. Frozen heavy water has a 10.6% greater density than ordinary ice. So normal ice cubes float in water, but heavy water ice will sink in water. As we explained in previous videos, the atomic mass is the number of protons and neutrons in the nucleus of an element. And since most elements exist naturally as a mixture of isotopes, therefore the value we use for the atomic mass of an element is an average mass of all the atomic masses of that element isotopes. But we should take into consideration the abundance of all naturally occurring isotopes in nature. This means if a particular isotope is present in nature in a higher proportion than the other isotopes, it will make a larger contribution to the average atomic mass. And this average value for the mass of an atom of an element is known as the relative atomic mass, and it's symbolized with the letter AR. So how can we calculate the actual relative atomic mass of an element? Let's take lithium as an example. Lithium has two isotopes, lithium-6 and lithium-7, and the relative abundance in nature for those two isotopes is as explained in this diagram. The diagram shows that the lithium abundance in nature is 7.5% of lithium-6 and 92.5% of lithium-7. What we need to do now is to calculate the mass of 100 atoms, and we can do that by multiplying the mass of each isotope with its relative abundance. The mass of lithium-6 is multiplied by the abundance of lithium-6 in nature, which is 7.5%, and we combine that with the mass of lithium-7 multiplied by its abundance in nature, so we get 692.5. And what we need to do now is to calculate the average mass of one lithium atom. We can do that by dividing the total mass that we calculated by 100. So we get 6.925, and that is the relative atomic mass of lithium and its isotopes. And certainly you can round that number to 6.9 for more accuracy. That was everything for today's video. Hope you find it helpful. See you again in the next video.